Hey guys, this is Mr. Lewis here. We're going to talk today about solutions and really focus on calculating the concentrations of solutions. So let's dive in. All right, so we've been discussing over the past couple of weeks the kind of introducing you to solutions, and we've recently focused on water and the different components of water, especially the review after our little spring break. And now we're really going to kind of dive into the math and the concepts of what makes a solution. So we've already discussed intermolecular forces. Now let's talk about calculating a solution. So there's a few terms we need to talk about first, and that's the terms we're going to talk about are solute, solvent, what a solution is, the difference between a soluble and an insoluble solution, and molarity, a unit of measure for concentration of a solution. We're then going to calculate molarity, and then I'm going to discuss how to make a solution, which I unfortunately wish we would be able to do in a lab and classroom, but we'll at least go over the math of it. All right, so our first terms are solution. So a solution is basically the liquid mixture of a component called the solute, which is the minor part of it, that is uniformly distributed within the major component we call the solvent. So the solvent is a liquid component that can be anything from like milk, water, an organic solvent like alcohol, acetone, or benzene. And the solute can be the thing that's dissolved in the solvent can be either solid or liquid. So if you think about dissolving making some salt water, you can dissolve salt that's a solid into the solvent, which would be water. Or if you had a liquid solution, say you had a syrup and you added it to some water to make it a little more dilute, that is also a solution. In this case, your syrup is your liquid solute, and water would be the solvent. So we're going to mostly focus in high school chemistry, we focus not on the organic chemistry nature of things, but more of the simple or inorganic chemistry. So we're going to focus mostly on water as our solvent. So when we talk about an aqueous solution, and you'll sometimes see the little AQ next to a compound name in a chemical equation, that just means aqueous solution. So it just means it's that particular solute that you're looking at dissolved in water. That's our solvent. And so how does that work? Well, let's see. Let's watch the video first.
When water-soluble compounds are added to water, they dissolve and form a solution, a homogeneous mixture of solute and solvent. When ionic compounds such as sodium chloride dissolve in water, the ions dissociate or break apart from each other and are solvated by water molecules. The positive ends of the water molecules, the hydrogen atoms, orient themselves around the negatively charged chlorine anions, while the negative ends of the water molecules, the oxygen atoms, orient themselves around the positively charged sodium cations. When molecular compounds such as sugar dissolve in water, the molecules do not dissociate. Instead, all molecules remain intact.
So again, you can see here with this little image here how we get the simple chlorine, negative chlorine ion associating with the positive charge in the water and the positive sodium ion associating with the negative charge from the oxygens in the water. So it's how that creates this kind of the water molecules create a buffer in which that keeps those ions separate, which allows for them to dissolve. All right, so now let's talk soluble versus insoluble. Soluble is really a substance that is easily dissolved in a solvent. So something like sodium chloride, when you add like a spoonful of salt into water, it all dissolves, so it is soluble. Something that does not dissolve in a solvent is called insoluble. So here we have that.
A substance is water-soluble if it dissolves in water. If it doesn't dissolve in water, then it is considered to be insoluble. Copper 2 nitrate is an example of a soluble compound. If we mix it with water, it will dissolve and form a solution. Copper 2 hydroxide, however, is insoluble. When we add copper 2 hydroxide to water, it does not dissolve. Instead, it remains as a solid at the bottom of the beaker.
So just because it's copper 2 hydroxide would actually be ionic compound, but doesn't necessarily mean it's going to be a soluble material. So we'll talk about solubility in no time and look at some solubility charts. So next I want to look at solubility and temperature. So temperature can affect, one, it can actually increase the amount of things that will dissolve in a solvent, but also how quickly. And that's because we're talking about kinetic energy. So let's get on that.
Let's compare hot and room temperature water. The first beaker is at 26 degrees Celsius. The second beaker is at 95 degrees Celsius. If we compare the two beakers with food dye added, you'll see that the dye distributes faster in the hot water. Why did this happen? The average kinetic energy of the water molecules is greater in the hot water than in the room temperature water. This means that the average kinetic energy of the particle is directly related to temperature. While the particles are moving faster in the hot water, not all the particles move at the same speed, which is why we take the average kinetic energy of the particles. We'll take a closer look at these concepts as we examine Maxwell-Boltzmann distributions in the paragraphs below.
No, we're not going to do that. All right, so next we're going to talk about molarity. Molarity is basically the unit of measure of concentrations for solutions. And molarity is simple enough. Molarity is just basically moles of the solute in the liters of the total solution, not the liters of the solvent, because that may change as you add more solute. You might get an increase or decrease in the overall volume. So it's the final volume of our of our solution. So let's talk about calculating, and I'm going to switch over to another screen in just a second, but we want to focus on so simple calculation of a solution contains 0.42 moles of solute and in 0.75 liters of solvent. So let's switch over to my document here. All right, so I have a solution that contains 0.42 moles of solute. Doesn't matter what it is. It's just moles of solute in 0.75 liters of solvent. Calculate the molarity. Okay, so remember, molarity, big M, is equal to the number of moles, we call that N, per volume in liters. So we just, so shorthand for moles sometimes is N. So that will give us molarity. So if we kind of create a little variable list here, we do not know what molarity is. N in this case is 0.42 moles. And our volume is 0.75 liters, which is great. So we can do our calculation by saying, okay, we have 0.42 moles divided by 0.75 liters. We solve to get divide both sides, or divide by 0.75 to get to 1 liter, and we end up with 0.56 molar. We don't call it molarity. When we tell you that, we say a 0.56 molar solution, which is the same thing as saying, you can sometimes say molar is moles per liter. So that's easy enough. So now if we take and look at the calculation of what if we don't know what the moles are. So in this case, I want you to find out what's the molarity of a 500 milliliter solution that contains 15 grams of sodium hydroxide. All right, so again, molarity is equal to N over V, where we have, which is basically moles over liters. So we create a little list of what our variables are. So molarity, we do not know what it is. Our moles, we don't know what those are either, because we don't have anything, we don't have moles up anywhere in our calculation, but we'll get there in a second. And we have our volume is 500 milliliters. Now let's go back to the moles. So we know we have 15 grams of sodium hydroxide. So we can write out and say we have 15.0 grams of OH. Now, we know how to calculate, we go from grams to moles using molar mass. So do a little dimensional analysis here. The molar mass of NaOH happens to be 40 grams per mole. So since I have grams on top and put grams on the bottom, these are going to cancel out. We're left with moles, which in this case will give me 0.375 moles. Now remember up here, we want our volume in liters. Right here we have milliliters, so we need to convert this into liters. So we're just going to again do some multidimensional analysis. We have 1,000 milliliters per liter. So we're going to divide 500 by 1,000, gives us 0.500 liters. All right, now we can plug in. We have N in moles, we have volume in liters. Let's go calculate it out. So molarity is equal to 0.375 moles, pardon my writing, and 0.500 liters for a final concentration of 7.50 molar. Make that a little neater. And that's our final answer. Simple enough. All right, let's go back over to our PowerPoint solution. And now we're going to continue on. Let's see, slideshow from our current slide, and talk about how wrong. That was the wrong one. All right, so how to make a solution. Make sure that we're actually looking at the right thing. No, I am not looking at the right one. Pardon this, it's got all messed up. All right, so from here. All right, so now let's talk about our last concept for today is how to make a solution. And so there's 4 simple steps. First, we're going to look at our word problem, determine what the concentration, final volume are needed. From that, we need to calculate the number of moles needed for that particular solution. And then finally, once you know the moles of the solute needed for the solution, you're going to calculate the mass of the solute. And then all you do is add the solute to what's called a volumetric flask. This is a very special flask that has a funky little shape like this. And it has a little line up on top. Unlike a graduated cylinder, volumetric flasks measure one and only one volume, but they do it very, very, very precisely. So that's why we use volumetric flasks. So we can add we add a little bit of water or water or whatever our solvent is into the volumetric flask. We add our solid, we get it all in there and start getting dissolved. And then all you do is you add the water up to the final mark, which should give you the perfect final volume. Get it mixed really well until it's dissolved, and you are done. So let's do a calculation showing that. So go back to my whiteboard here. Oh, come on, show my whiteboard. All right, I have way over here. I want to prepare a 100 ml solution of 0.10 molar NaCl. All right, so remember, molarity is moles per liter, which again is N over volume. All right, we know what our molarity is in this case. It's 0.10 molar. And we're not sure of yet. And eventually we want to take that to grams. And our volume in this case is 100 milliliters. And if you remember, we want our volumes to be in liters. So let's go ahead and just convert that right now. So we have 1,000 milliliters per liter gives me 0.100 molar. liters. So now we can calculate N because we have our volume in liters and we have our molarity. So in this case, we have 0.10 molar equals N over 0.100 liters. Multiply both sides by 0.1, and we end up with N equaling 0.010 moles. Well, that's great, but we can't actually it's really hard to measure out moles, so we can measure things in grams. So we're going to convert moles into grams. So I'm going to take that 0.010 moles, again, of NaCl. And now we're going to multiply it by the molar mass, grams over moles of NaCl. That'll give us grams NaCl. I'm just going to drag this over a little bit. Molar mass of NaCl is 58.44 grams. And if we multiply that out, we end up with 0.5844 grams of NaCl. And if we are looking at sig figs up here, we have 2 sig figs in our molarity. So I would say this is 0.58 grams. That's our final answer. So we would take the 0.58 grams, put it into a volumetric flask, and bring that up to 100 mils or 0.1 liters. And we're done. So that's how we make a solution. Similarly, if you don't know volume but you know grams, you can convert from grams to moles. And then if you know the molarity, you can know how much volume you can create. If you know all the different calculations, it's just finding what the unknown is and doing the algebra to calculate to get there. So hopefully this gets you to an understanding of how to do the different calculations that you're going to be doing on the molarity worksheet. So look at the next assignment in Schoology below this video, and do the 10 questions that are associated with that. If you have questions, again, shoot me an email, or if you need to walk through them, again, my office hours are going to be on Friday. Just shoot me an email early enough and we can go face-to-face and go over some of the answers. The worksheet doesn't have an answer key yet, but I will post it by Thursday night for you guys. So hopefully that's everything we need to cover, and have a great day. Talk to you later. Bye, guys.